Well, we're back at it again. Welcome back to Algebra, grade 6 through 8. Again, we're using the Spectrum Algebra workbook available on Amazon. I recommend that you get that book to get the most out of these videos. Today, we're starting chapter 3. We finished up chapter 2, so it's a natural thing to move on. So, today, we're going to be talking about factors. And a lot of times in math, it seems complicated because there's a language that goes with math. And the faster you incorporate that language, the easier it will be for you to understand problems and, in fact, appreciate them. So, we are on page 21 of the book, lesson 3.1. Before you do this video, pause and read this section yourself. I'm not going to read word for word, but we're going to talk to it. So stop it and stop the video and come back if you need to. So a factor is a divisor of a number, and the result is that you get whole numbers in response. So at the top you see 15 and 12 right here on the right. We know that if we divide 15 by 3, we get a 5, which is a whole number. We know if we divide 5 by 15, we get 3. So if we were to just think about that in terms of the definition, 3 and 5 are factors, and what's not shown here is also 1 and 15 are factors. So it's any number or a divisor. It's any number that when you divide into the number, you get back a whole number. So let's take those two examples we just did. We have 12. So when you think of factors, you think, okay, what divided by 12 gives me back a whole number? Well, 1 divided by 12 gives me a whole number. Well, 2 divided by 12 gives me 6. Well, 3 divided by 12 gives me 4. Well, 4 divided by 12 gives me 3. What else? 5? No, 5 will go into 12, will give me a remainder. It's not a whole number, so that doesn't count. Well, 6 divided by 12 will give me 2. And what about 7? What about 8? So now you're doing this really quickly. If you know your math tables, you'll know that when I'm going through 7 doesn't go into 12. There's nothing times 7 that will give you 12 except for a real number or a number that has a decimal or remainder. No whole number will give you 12. So we do 8, we do 9, we do 10, 11 we know, and so the last one is 12. And so I shouldn't say equal because it's not an equal sign, so I'll say it gives. Now we're factoring. And then the other number we wanted to do was 15. So we can go through that process again. 1 divided by 15 is 15. That's a whole number. 2, no. 3, yes, I get 5. 4, no. 5, yes, I get 3. So I'm starting at 1 and going up in the numbers until at least I get to that number 12. If I did 13, you already know that you're not going to get a whole number, right? That will be a fraction. So you stop at the number itself. And so I can do 6, no. 7, no. 8, no. 9, 10, no. 11. You keep going, so you get 1, 3, and 15. Then they have another term here called the greatest common factor, and that's described right here. It's the largest number shared by two numbers. So you might have, if you want to know the greatest common factor of these two numbers, what is the largest number that they have in common? Correct. The greatest common factor here is what? Look at the two lists on the left. It's 3. So if I was looking at 12 and 15, the greatest common factor is 3. So you might say to yourself, well, when would I use this? How about if you want to reduce this fraction? If I use these numbers as fractions, saying 12 divided by 15 or 12/15, and I wanted to try to get this in its lowest form, if I had this common factor 3, I could use the distributive property, which we talked about, and pull it out. So I said the distributive factor could be used to simplify, and it could also be used to factor. So we showed it in the last video using with respect to algebraic equations where you had a variable, a number, and an operator, but now we're just doing it with fractions. And so if I pull it out and I write it this way, what would go on the inside of this parentheses? 4 over 5. And if I divide any number by itself, the answer is 1. So 3 over 3 is 1. So this term would go to 1. And 1 times anything is that quantity itself. So I could use greatest common factors, for example, to reduce a fraction. So when you start saying, well, why do I have to remember greatest? Because there are several common factors. 1 is a common factor. But if I want the largest common factor, that's 3 for these two set of numbers. So when you talk about greatest common factor, you are talking about the factor that the divisor that the two numbers have in common, or the factor. So 3 is that number here. And remember, divisor, we want a whole number in response. We don't want a number and it's a decimal. Okay. So then this, in the example, goes on to show how you could do this for two numbers, 32 and for 40. So you could see they did the same thing. You could see if I know 1 times 32 is 32, 2 times 16 is 32, 4 times 8 is 32, and I write them all out, I now get the factors. And I do the same for 40. Now if I say what is the greatest common factor between these two, the one on the left, 32 and 40, we can quickly see that that's 8. So the advice here is when you do these problems at the bottom of the page, actually list out the factors and think in your mind, okay, 1, 2, 4, these numbers help you to get the greatest common factor. And the way we did it here was we started with 1 into 12, 2 into 12, 3 into 12, 4 into 12, 5 into 12, no, 6 into 12. That's how we did it. So they show it the same thing here. All right. Now the next thing we are presented with is this term called a prime number. So the definition is right here. Any number that's greater than 1 and it only has two factors. And what two factors are they? The number in itself. So some examples of prime numbers are 2, 3, 5, and 7. Let's check 7 since it's bigger. Does 1 go into 7? Yes. Does 2 go into 7 without remainder? No. 3, 4, 5, 1, and 7 are the only two factors that the number 7 has. And you can, so they have some other terms here, right? And a composite number, I'll let you read these, but basically they're trying to relate back to the number of factors. And so they're trying to, when you do factorization, you know you have gotten it all the way when you get down to prime numbers. Why? Because prime numbers only have two factors, the number in itself, and they have to be greater than 1. So a composite number has two factors. For example, 4 has 1 and 2, and 4. A composite number can be written as a product of prime numbers. So you could write as 1, 2. Yeah, that's the only way you could write it. Prime factorization is the idea of taking this number 45. You break into 5 into 9. 9 goes into 3 and 3. 5, 3, and 3 are prime numbers. So that if you build this tree, the last step is to have prime numbers. So that's the idea But the thing you want to remember here, you want to know what a prime number is, but you most of all want to be able to use this to do problems. And so we showed, here we showed that it could be used to factor. It could be also used if you're trying to solve an equation. Like, I want to try to simplify this, and I want to rewrite the right hand side. If I know I can pull 3 out, it's actually a factor of 12 that I'm using to pull out. 3. 3 has common to 3x and is common to 12. Distributive factors say I can multiply this through. If you remember, we learned that with the distributive property. So I'm trying to say to you that when you find these factors, you'll be using it to manipulate a pair of numbers. It's always 2 numbers. There are 2 numbers here that we're considering, 12 and 15. And in the case of reducing a fraction, you might see it in this way. In the case of the equation, you might see it as presented here. All right, so let's keep going. That was 3.1. So now we'll go to 3.2. All right, so if you recall, we talked about power and exponents, or maybe you just were introduced to that in school. So we'll do just like a quick refresher so you'll understand what that's about. So when we write a number like 2 to the 4th, 2 is called the base. 4 is the exponent. By the way, this exponent is positive. What does this really mean? It's a compact way of writing 2 times 2 times 2 times 2. It's a compact way of writing this expression. And when we have something, we would say this is 2 to the 4th power. If we wrote this, we say this is 3 to the 2nd power. If we had this, we could say this is 5 to the 3rd power, etc. So we have some definitions. This is the base. This is the exponent. We call this a certain way. So just as we call this as the power. So just like we did in the previous section, stop the video and read this. This will really help you. Okay, so a number multiplied by itself can be written in this compact form, and there's language that goes with that. We have a base, we have an exponent, we have the power. When we have something to the 2nd power, it's called squared. When it's to the 3rd power, it's called cube. When it's to the 4th power, you say to the 4th power. People might use the language a number raised to the power. So raised to the 2nd power, raised to the 1st power. We know that any number to the 0 power is 1. That's a review. When we did exponents, you probably saw that already. So if I have 105, sorry, that's crooked, to the 0 power, if I have this base and I don't multiply it by itself, what this says is you get 1. If I do 105 to the 1st power, that means I have one of them, then you get the number you started with, 105. So this is key to remember. You might have forgotten this, but any number to the 0 power is 1. Any number to the 1st power is the number that you started with. That's a little review. So you'll have equations that have exponents in it, and they give this example. We're now in the last part of the paragraph. Let's skip ahead to try to see if we can work that problem. So I'm going to read it to you. Take your pen and try to write it. 2 squared plus 5 squared. That's right, 2 squared plus 5 squared. So now we already talked about this being in compact form. So if we had to evaluate this, we would write 4 plus, what's 25? 5 squared. Sorry, I gave it to you, 25. And so we know this answer would be 29. Now, if you notice, when I'm writing, I'm going line by line. I started with the first line, which is the problem. Each term, I substituted down. I brought the operator along the way. This is 25. This 5 is right next to the 2. And we resulted in 29. Now, there's some interesting things I want to mention to you. When you have a parenthesis, unlike when you have multiplication outside of a parenthesis, when you have this to the second power or any power, you cannot distribute the power internally, which means you cannot write this as 2 squared plus 5 squared. When you have a parenthesis like that, you must write the whole parenthesis, because that's truly what's squared. We learned previously, and I think we learned this previously, our order of operations. We know that it will be bracket, parenthesis. Now we're just reviewing bracket, parenthesis is on the same level. Do whichever one is on the inside first and working, then from left to right. Then you know that it's multiplication and division. That's second. And then we know that it's plus and minus. Order of operations. So by the order of operations, I cannot just distribute this. I have to do the parenthesis first. And so you would have to multiply these two terms, and this does not equal this, because if I add these two on the inside, I get 7 times 7. And what would that be? 49. 49 is very different than 29. It is not the same answer. Okay. So going back, that's actually discussed down here in this last chapter. You cannot use a distributive property. You cannot just go inside the parentheses and apply it. So at the bottom of the page, there's several examples. I think they're pretty straightforward. We'll pick one or two here to do really quickly. And so we'll be looking at problem 3. All right, so 3 to the 4th and 3 to the 6th. You actually do this calculation. You figure out what this is. 3 times 3 times 3 times 3, and this is 9 and 9. This is 81 plus, and then you do it again, so I can see that there's 2 more here, so this would be 81 times 2. And I don't expect you to do it this way. I'm doing it real quick. Excuse me. This would be 9 and 9, 4, 89, 81 times 9, not 2. So I would probably do 81, and then I'd put 1 plus 9, because I'm doing this without a calculator, which you can do 2, and you get the answer, which should be 810. I might have made a mistake, but the key point is here is do each term. All right, I picked a hard one. Let's pick another one. So the other problem we'll do is 2b, which is 3 plus 1 cubed. 3 plus 1 to the second power. That's how it says, say 3 to the 4th power plus 3 to the 6th power. So this is 3 plus 1 to the 3rd power on the right hand side, and we're trying to solve that. So what we already just said is you can't distribute. I just can't say 3 squared plus 1 squared. No, cannot do that. Instead, I have to write out 3 plus 1 times 3 plus 1 times 3 plus 1. Now the good thing is we don't have any variables in here, because we have variables a little bit more complicated. If not, because they're not, I can just say this is 4 times 4 times 4, which is 16 times 4. And you could take it the rest of the way to get the answer. Okay, let's do it together. So 16 can be written as what? 10 plus 6 times 4. So this is 40. If I multiply this times 4, I get 40. And 24, I can quickly get the answer. And I get 64. So I did use mental math. Now you could use a calculator, but I could see that this term could be written as 10 and 6. I know anything times 10 is very easy to get, and I just multiplied it. That's not required, but that's just a little review in mental math. All right, so that's 3.2. Try those problems at the bottom. I think you should be able to do them now. 3.3. All right, so here we go. We are thinking of a way of simplifying and reducing fractions to their lowest terms. And we just started talking about how that could be done. So you could do the factors. And if you do the factors, you're able to see that 20 is common. You can pull out 20. 20 over 20 will give you 1. You get 3/4. That's sort of like what we were just saying. But let's look at this at the bottom. Well, hopefully you understand what I'm saying here. Let's just, 60 over 80 is equal 60 divided by 20. So what did I do? I did the factors. I got the greatest common factor. I pulled it out. 20 over 20 is 1. The way this is written, let me write this way so you can see it. So we started with 60 divided by 80. We figured out, we figured out what was the common term, which is 20. We pulled it out, top and bottom. And what do we get? 3 over 4. This is multiplied. So 3 times 20 is 60. 4 times 20 is 80. This is factored in its lowest term. And that's what they did here. But you could have something that's more complicated, that is more of an algebraic expression. So we could have 12a squared. You know what? Let's just clear this because we're going to need the room. 12a squared, or a to the second power, over 15a. So we already said that when I write 12 times a variable, that's the same thing as saying 12 multiplied by the variable. And we already said that 12a squared is really 12a times a. And we can also do the same thing in the denominator. We know that this is 15a. But what if I wanted to reduce this fraction? I'm trying to simplify this. So I would say, well, what's the common factor between 12 and 15? Oh, excuse me. So you go off on the side and you do the same thing we did before. 12, we got 1, we got 3, we got 4. There's commas in here. We have 12. Now for 15, you go off on the side and say for 15, we have 1. We don't have 2. We have 3. We have 5. You know, you do it on your little scratch paper. Then you come back over and you say, okay, I'm going to pull out 3 using the distributive property. And so I'm going to end up with 4a divided by, I'm doing it to the top and the bottom. So I get 5 on the bottom, 5a. So 3 over 3 goes away and we get a over a. So we have 3 over 3. I'm rewriting just so you can see, but after a while you won't have to do this step. You'll see it. A over a times 4a. Come on. My hand is killing me. Over 5. And so 3 over 3 goes to 1. A over a goes to 1. So we end up with 4a over 5. Okay, again, let's review. So what we did was we started with this fraction. We want to simplify. We try to find a common term, the greatest common term. We talked about that's why we learned that before, so we can do manipulation like this. We understood that to be 3. We pulled that out and we expanded the exponent. We just learned the exponent is a times a, so we wrote it that way. Then we rewrote it so that we have anything over anything, like 3 over 3 is 1, a over a is 1. Why? Because 3 over 3 is really a statement of division. 3 is really saying 3 goes into 3. How many times 1? So any number over any number, any variable over any variable is always 1. So this is the result. And there are several really good problems on this page. I encourage you to look at those and try to work through those. And I would say on this section, really spend the time to do that. There's a lot of problems here, but you get a lot of good practice before we go on to 3.4. All right, so in 3.4, this is a little trick that it's not really a trick. It's something that is useful when you have very complicated problems. So you start with a common base and you multiply two numbers that have the same base. We already said what the base and exponent of a number is. And so what we're showing here is 5 cubed times 5 cubed. If you wrote it out, you'd have 3 5s on this side and 3 5s on this side. And if you just combined it together, you really get 6 5s. Right? These are supposed to be 5s and not S's. And these are all multiplied. So these 3 work with this 5. 3 go with this 5. But in doing that, you could easily see that that is the same as adding exponents. 3 plus 3 gives 6. So once you know this, you can use this. It's very valuable because when you have very complicated expressions, the requirement is it has to have a consistent base. The base here is 5. The exponent can be positive or negative, but it has to have a common base. Let's write that. The trick here is you have to have a common base, and the operator has to be multiplication. For example, this does not work with addition. This does not work with addition. This is true for multiplication, and you will see for division. All right, so you can actually do problems really quickly. If you look at the example they have here, 10 divided by 10 squared is really going to be 6 minus 4, and you will get 2. If you write out all these 10s, these two 10s go together with these two 10s, and that goes to 1. You get 1, 2, 3, 4 10s left. So again, that would be like 10. Come on, sorry. That would be like 10 to the 6th power divided by 10 to the 2nd power. Because it has a common base, the base here is 10, would be 10 to the 6 minus 4. You could actually write out all the 10s like we did in the previous problem and show this. And I suggest you do that when you go through the example so you can convince yourself. Now the next page, which is 3.5, is going to start talking about negative exponents. And before we actually read the page, if you have anything where you have 1 over, these things, this is true. You can write 1 over, or you can write 5 to the minus 3. These things are interchangeable. I said these things are interchangeable. So if I did this problem before, 10 to the 6 divided by 10 squared, what do I have here? I really have 10 to the 6. I can also write this as 1 over 10 squared. Just take a look here. You can see that this does in fact equal this. 10 to the 6 over 10 squared is the same as 10 to the 6 times 1 over 10 squared. As a result, I can write 10 to the 6, and then I can write times. What would this term become using this known thing I'm just showing you? I can go this direction, take it from this form to this form, or vice versa. So I can write 10 to the minus 2. Then it's just like the problems I did before. I add the exponents. In this case, 6 minus 2, I get 4. 10 to the 4. So that skips us along to 3.5. And in this one, they're actually showing that before you get caught up in the 1 over 25 and all that, converting to decimal, I want you to see that 5 to the minus 3 means 1 over 5 cubed. And if I'm able to do that, these examples here at the bottom shows that because I have a common base, I can just add up the exponents using the same thing that we learned in the previous chapter, negative number and a positive number. If you add two negative numbers, right, you get a negative number. Minus 3 and minus 2, you get minus 5. You see how things are building? Like if you really understood how to add two negative numbers, this would be very straightforward. We also showed that when you have a negative number that's larger than a positive number and you're adding them, the result takes the sign of the larger number. That was a rule I gave. Those things follow through. So if you're having problems understanding, make sure you understand how to add and subtract negative numbers of what we kind of discussed previously. And there are several problems on this page. I invite you to take a look and always remember the key factors here, which were you have to have a common base and you have to be multiplying just to add those terms. I think I actually erased that whiteboard. All right, so we're going to go on to the last one. I know it's getting a little long. Okay, scientific notation. So this one, we just want to try to talk through this. Why do we have scientific notation? How many of you guys have iPhones or what is the other phone? Android devices. And you are playing Xbox or you are playing something or you're working with images and movies and now your phone is full. When you look at your phone and understand how much storage you have in your phone, it reports back to you in terms of gigabyte. Giga is a unit of to give you a measurement. So giga means 10 to the positive 9. Let's go to our whiteboard. This is a big one. Don't forget this. Even though we're transitioning to the next topic, make sure you understand and learn that. Okay, so we know giga is times 10 to the 9. And so when people talk about bytes or how much storage is left on your device, they say gigabyte. And giga is 10 to the 9. It's a very long number. That means 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. That's 9 zeros. Woo, that's a lot. That's 9 places. Ones, tens, hundreds, 10,000, 100,000, blah, 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 blah. Anyway, just the point is this is a huge number. If I was to give you like a number with a 5 in this place and a 3 in this place, this is very hard for you to really work with. So what people do instead of doing this is they write a term gigabyte. That's really like a scientific term. That's a scientific notation. So when you have numbers that are really big or numbers that are really small, and you need a concise way to write it, you can write it in scientific notation. And people will often do this if you're taking measurements of things. The other application is if you want to measure how big, like the diameter of your hair, one single piece of hair is very small compared to measuring the diameter of your finger. Look at your hair, pull out a strand, look at the size of that, and then look at your finger. Whatever kind of thing you're going to do that measurement, you see that these are on vastly different scales. So to be able to compare or do anything where these numbers have some semblance, you have to have scientific notation. And you'll see that as you go along, and it's so popular that people use it all the time. Like you use centimeter to talk about what size of a meter. A meter in itself is pretty big, but a centimeter, if you have a rule, is very small. It's 1/100th of a meter. So there's a lot of use of scientific notation. It's hard to see right now, but the key thing is that if you understand how to go back and forth, like this example, 1503, which is 1503, can be written as 1.5 times 10 to the third power. And so if I had a whole bunch of numbers like this and I wanted to add them up, instead of having 4 places, I might change this order. And you, over time, you develop, when do I want to use it and when I don't want to use it. Right now, they're just introducing the idea so that you will have a feeling for there is alternative ways to write numbers. If you write it in the way here on the left hand side, that's called the standard form. If you write on the right hand side, it's called scientific notation. Whenever you write in scientific notation, you always have 10. It'll either be to a positive number. If you've moved the decimal to the left, the decimal was behind 3. We moved it 1, 2, 3. Let's just show it on the whiteboard. 1503. The decimal is actually right here. If I write in scientific notation, I move the decimal over 3 places. For these two numbers to be the same, I'd have to multiply this by what? 1,000. What's another way to write 1,000? You can write it as 10 cubed. 10 times 10 times 10. So the point is that this number does in fact equal, these numbers are in fact equal. They're just written in a different form. This top form is called standard. This bottom form is called scientific notation. You can do the same thing if the number is less than 0 and you want to get it where it's more like 3 point something, where it's not so small. You can do that as well. So we have 0.03 point. Now decimal is right here. So if I want to write this number where the 2, where it'll be 3 point something, but I want to move the decimal over 2 places. But if I do that, I can't just do that. I have to have a minus 10 to the minus 2 for these two things to be equal. The scientific notation is not trying to rechange the number, it's just trying to change the form of the number. But these two sides still have to be equal. All right, so then there are several problems to try, and we are at the end of chapter 3. I hope this was valuable. It may seem like a bunch of hodgepodge, but what I've been trying to do is show you what's coming and show you why we learned things in the past. Remember, math is fun. Until next time, thank you.